Okay, let's show the convergence property of proximal gradient descent approach. So for this, from this slide, I will use GXT to denote the generalized gradient. So in the previous part, I used the notation GH gamma X to denote the generalized gradient. But from now on, I will just simply use GXT just for simplicity. Okay, and let's assume G is beta smooth. So when G is beta smooth, again, I will set the step size gamma equal to 1 over beta, and I will analyze with this learning net, we will have very nice convergence. And from the beta smoothness, we have this inequality, right? So that comes from the beta smoothness of function g. And so from the definition of function f, because fx is equal to gx plus hx, we can have the first inequality, right? And from the convexity of function g and h, we have this second inequality. So gxt is upper bounded by, for any z in your input domain, gz plus gradient of gxt transpose xt minus z, and ht plus 1, hxt plus 1 is upper bounded by hg plus gradient of ht plus 1 transpose xt plus 1 minus z, if both g and h are differentiable. But the problem is, as I explained earlier, h function can be non-differentiable. That's why we have to use proximal gradient descent algorithm. If both g and h are differentiable, we don't need to use proximal gradient descent algorithm. You can simply use gradient descent algorithm. So this is typo, actually. We cannot define gradient of h at some point. Instead, we can use subgradient. Okay? So I will explain what is subgradient in different video clip. Right. And from this second inequality, when you rearrange these terms, we finally have this fg plus the generalized gradient gxt transpose xt minus z minus 1 over 2 beta generalized gradient gxt normed square. Okay. So from the last equality, we can have two very important and interesting inequalities. So when we set z equal to xt, we have xt minus fxt plus 1 greater than or equal to 1 over 2 beta gxt normed square. This is sufficient decrease inequality. So previously, without this h function with simple gradient descent approach, we have this fxt minus fxt plus 1 is greater than or equal to 1 over 2 beta gradient of fxt normed square. So we have almost the same inequality. We just replace this part, gradient of fxt normed square, by the generalized gradient normed square. When we set z is equal to x star, the optimal point, we have this fxt plus 1 minus fx star is less than or equal to gxt transpose xt minus x star minus 1 over 2 beta gxt normed square. And from the definition of this, So gxt was equal to what? 1 over gamma xt minus xt plus 1, right? And you can use simple equality. You can rewrite this term by this with these two. So as we did in vanilla analysis for gradient descent approach, from this generalized gradient, we can write down this. Okay, and also from the definition of gxt again, we can replace this term by gamma times gxt. And since gamma is 1 over beta, we can remove this one using this one. So in the end, we have this fxt plus 1 minus fx star is less than or equal to beta over 2 times xt minus x star norm square minus xt plus 1 minus x star norm square. Oh, sorry, this one come to here. Okay, it's good. We have our ingredient. From the sufficient decrease property, we know that fxt plus 1 always less than or equal to fxt. So which means 1 over capital T summation fxt minus fx star from t equal to 0 to capital T minus 1, or t is equal to 1 to capital T. This is less than or equal to fx capital T minus fx star, and this is less than or equal to beta over 2 times 1 over t times x0 minus x star square. Okay, because I just sum all fxt minus fx star, then basically this part canceled out each other, and we can simply ignore this negative part in the end because we are interested in the upper bound. Okay, so in the end we have fxt minus fx star is upper bounded by beta over 2 times 1 over capital T times the initial radius, initial distance. So with non-differentiable function h, in that case, we cannot use previous result, very nice beta smoothness and their convergence speed, because h function is not smooth and non-differentiable. But with proximal gradient descent approach, we can utilize all the previous result.